This evening, I'm pleased that we're going to have a non-expert introduction to AI, because I feel like myself, there's probably a lot of non-experts in artificial intelligence in the room. But I'm pleased to introduce a colleague of mine, Rafael Perera, who is medical statistician in the Department of Primary Care and runs a significant, large medical statistics group in medical sciences, and has particular interest in application of healthcare in primary care and the use of data sets and artificial intelligence. So thank you very much, Rafael.
So thanks everyone for inviting me to talk today. Thanks to Professor Vinci, to Carl, also to Dr. Richards for the invitation and the support to give this talk. I am particularly pleased to be here. It's really an honor to be presenting at Kellogg during Bletchley Park Week, celebrating the achievements of obviously many people in Bletchley Park, all the women and men who produce work that has profound impact on all our lives. Me as a statistician, simply I can say that my job would not be feasible without the advances that were made there, and I'm sure that everyone pretty much our lives would not be possible without them. As I said in my slide, I'm a non-expert. I have used quite a lot of the methods that have been proposed as part of artificial intelligence, but I cannot claim to actually do this as my bread and butter, let's say. At the same time, I think that there's a bit of misunderstanding about what AI is in general. So I'm hoping that with this talk, I'll be able to present my understanding of AI. It's been obviously, for preparing this talk, I've extracted material from many different sources. And if I have made any mistakes, I apologize beforehand, and I'll be very happy to be told that, what I need to correct. But it gives you an overview. I'm hoping to give an overview of what AI is about. This is an outline of the talk. I'll give a brief definition of AI. I'll talk briefly again about its history. I'll touch on the questions that AI is trying to solve and the basic approaches, particularly, of how it tries to solve these questions. And finally, I'll mention why AI, where we are today, and the applications specifically in healthcare, which is the area that I'm mostly involved in. So I'm borrowing, first of all, a definition of AI by Professor Jeff Aronson. He is a great user of language, and one of the things that he accurately pinpoints is that the definitions that are commonly used for describing AI, finding AI involves intelligence in some form, which by definition actually produces a non-standard or circular definition. Instead, this definition talks about, first of all, a branch of computer science, which in a way highlights where it started in and where most of the initial applications and developments happen. And it involves the ability of a machine, not only a computer, but typically a computer, to emulate specific aspects of human behavior and to deal with tasks that are normally regarded as primarily proceeding from human cerebral activity. So in a way, we're talking about intelligence, but going around the issue. In popular usage, when we talk about AI, we refer to the ability of a machine to mimic the capabilities of a human being. And that means things like, for example, recognizing objects, understanding and responding to stimuli that happens, and making decisions and solving problems. And generally, we can think of AI as thinking of these machines performing functions such as greeting hotel guests or driving a car. So I'll touch a little bit about where we are regarding these applications. But if we think of AI, probably this would be the immediate pictures that we would have. Sentient robots. In popular culture, we have this view of machines that think and behave like humans. And on one side, we have Terminator, and the other side, we have R2-D2 and C-3PO as, in a way, machines that we would be interacting with. In reality, AI it's actually quite far away from these examples. Now, whenever we talk about AI, we definitely cannot go through it without mentioning Alan Turing. And there's two basic aspects of why he is involved in whenever we discuss and interpret and discuss the history of AI. The first one is the his approach to, I hope I'll say this right, the Entscheidungsproblem, which was a problem set up, I believe it was in 1938, Hilbert. And the idea behind this problem was to understand if there was a way of decision making by using just logic to interpret whether the results could be a true or false for a theory. Now, what Turing did with this initial paper was to hypothesize a machine as a theoretical construct that we use basic rules to decide whether the question could be answered or not, and show that the solution was basically no, it wasn't possible to actually answer this question. But the important side of it is this theoretical construct, which is not atypical in mathematics. We very often have situations of, well, what happens if we have this particular hypothetical thing, in this case, a Turing machine, and if we use it in such a way, would we be able to develop, in this case, answer the question of decision-making problem, which was incredibly important because we basically now use these Turing machines are the hypothetical and theoretical precursors of the computers nowadays. The second item is in 1950 was the use of Turing of the term artificial intelligence. The term itself, artificial intelligence, was not coined by him. Got the name of the person who did it. It was in 1945, and I'll come back and I'll tell you about it later on. But he used this term in order to describe what would be a situation, a machine that would possess artificial or intelligence in order to mimic responses, mimic human responses under specific conditions. And he was interested in things like, for example, being able to play chess. That would be a classic example of intelligent behavior. But he went a step further and proposed a situation where, although we might not be able to tell that or to verify that someone possessed this artificial intelligence, he proposed changing the question instead to whether a machine was intelligent, as to whether or not it's possible for machinery to show intelligent behavior. And basically, the way I would explain it is, if it looks like a duck and swims like a duck and quacks like a duck, well, it's very likely that it's a duck. That's his approach. If we cannot tell the machine apart from a human, then we decide it has emerged as having artificial intelligence. And this led to what is called the Loebner Prize, which is a contest, I think it's held annually. It's a contest on competition on artificial intelligence that awards prizes to computer programs that are considered to, by the judges, to be the most human-like. Turing believed that this test, which people know as a Turing test, would be solved or would be passed by the year 2000. Here we have, I'm just presenting an example of a program called Eugene Guzman, apologies, developed in the year 2001. It's actually finished in second place in this Loebner Prize in 2005 and 2008. It's supposed to simulate a 13-year-old Ukrainian boy to allow some degree of forgiveness for grammatical errors and some lack of general knowledge. So you can go into this website, the Eugenio Guzman elasticbeanstalk.com, to actually interact with this robot, this program. And what you can see here is my interaction with him. So I first of all, say hello. Hope you enjoy our conversation. He replies. I just ask him a question. Do you like ducks? Does anyone hate it? Could you tell me more about place? I'm sure it's a beautiful place. It gives us such beautiful people, etc. As you can see, from my perspective, it didn't pass the Turing test in this particular example, but I'm going to show you in a longer presentation. You're very welcome to interact with. And this was in 2005, 2008. So maybe we're not there yet. Part of the problem, I would say, is that the Turing test and the Loebner Prize have caught the imagination of people. And the program, and the reason why I say it's a problem, is the programmers have developed different techniques to try to cheat or try to trick individuals to believe that they're actually having a conversation with human beings, which are not really developing or furthering our understanding of artificial intelligence as such. So it's a bit of a gimmick, to be honest. And most people that are working in AI are not really interested in solving this particular type of issues. Now, it's important to try to understand what a computer does. As I was saying before, the use of a Turing machine, which was, first of all, a paper hypothetical construct, turned up or developed into the computer machines and computers that we have nowadays. So the phones that we carry everywhere, the thing that I'm using to actually do this presentation. And computers, what they have is this ability to follow instructions. And computers nowadays, they follow a myriad of very complex instructions, but it could be instructions as simple as 5 + 5, as what is the product of 3,456 times 7,890, print the word hello world. For anyone that's been a programmer, you know that that's the first program that you write, make a beep, etc. And it does this incredibly fast, very, very fast, about 100 billion operations every second. If we think of an operation, a human taking about 10 seconds per operation, 5 + 5 or 3,000, blah, 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 etc., it would take us around 3,700 years for what a computer does in exactly 1 second. And that takes us back to around the time of Moses. And it doesn't make many mistakes. Sometimes there's a few mistakes, but not that many. And because of this, we basically have a machine that is incredibly powerful. One of my favorite writers, Douglas Adams, talks about a computer and trying to understand what it is. Initially, we thought it was a calculator. Then we thought it was a typewriter. Then we thought it was an account sheet or a personal assistant. It isn't. It's a modeling device. And hence, it's very, very flexible. And hence, we think it can do absolutely anything. And that's why the promise of AI or artificial intelligence comes in. In some ways, we've been here before. In fact, AI has a long history of being the next big thing. Since the initial discussion of AI in the 50s and the 60s when it first appeared, there was a perception that it would solve many of the issues in the first. Well, initially, I can't remember the name of the person that invented the term, but he thought that within 2 months they would be able to solve many of the problems of artificial intelligence. Clearly, that was not the case. And as you can see in this graph, there's been periods of incredible growth, and at the same time, periods of what they call the AI winters 1 and 2. We can think of the development of AI linked intrinsically to the development of the computer. And maybe most of you have heard of Moore's law, which states that and he stated in around 1965, where he said that the number of components in a computer would actually double roughly every year for the next decade. A decade later, in 1975, he said, well, it's going to double roughly every 2 years. And it's actually the power of computers have doubled up roughly every 2 years ever since to nowadays. It's beginning to plateau, but we're already able to do significant amounts of really pretty complex and interesting things with the computer power that we have nowadays. The other reason, and this is probably the explanation for the explosive growth in the last 20 years or so, is that we now have incredible amount of information available. We're so interconnected with our devices that we're producing so much information that feeds into these algorithms, into these systems, to allow us to make predictions about what's going to happen. More about that in a second. So where are we? Well, first of all, this in a way presents a list, thanks to Michael Woolridge. He's a professor of data science here in the University of Oxford. He was actually, I think up until recently, the head of the department. He presents these examples of the type of problems that we've tried to solve with artificial intelligence, and the ones that have been done appear in the column on the left. So arithmetic, sorting list of numbers were relatively straightforward. And then there were some issues or some effort needed to be done in order to play simple board games, playing chess, recognizing faces in pictures. Nowadays, we obviously have a phone and our faces recognized pretty much immediately, which is incredible. Usable automated translation, playing Go, and then usable real-time translation to spoken words. Almost there. Things like driverless cars. So there's a lot of them, or quite a few attempts around our, so not our streets, but some of the streets, particularly in California, I believe. But they're actually still not 100%. There might be an issue regarding what is our threshold for safety in things like driverless cars, and things like automatically providing captions and pictures. And things that are not nearly solved are things like, for example, understanding a story and answering questions, human level automated translation, interpreting what's going on in a photograph, writing interesting stories, interpreting a work of art, or human level general intelligence. That last point might be a bone of contention to decide whether that's actually feasible or not. Now, the reason for where some things have been solved and other things haven't, and some things have taken a bit of effort and others were relatively quick, is because there are some of these tasks for which we can create a list of actions that a computer can do. And in those cases, we can think quite clearly of a way of creating or transferring this list into a computer, and a computer just have to run these actions. Having said that, sometimes the list of actions is so huge, as I'll explain in a second, that even with the most powerful computers, it might be quite challenging to carry out these tasks. At the same time, there are some things that we have no way of, at the moment at least, of understanding how to create an automatic list, or in order to feed that into the computer to achieve that, that task. And that's why the nowhere near solved are in that place. So these are the general questions at the moment that AI is trying to solve. We can think of these 8. First one is knowledge representation. We can think of that as the collection of information, like an encyclopedia, that can be used to identify potential interlinks between these knowledge. Second one is planning. I think that's relatively straightforward to understand. Things that will help us with decision making. For example, all the maps that we carry, or the in our pockets nowadays. Not the maps, the algorithms to take us to a particular place, wherever we want to go. We have aspects about learning, so using devices to learn or to teach about specific aspects. Natural language processing, which allows us, or it's about being able to receive information using language as well as generating information the same way. Perception, which is about capturing information from the outside world. Motion and manipulation, which is moving in the world. So these are all the things that computers are, or people that are working on artificial intelligence in general, are trying to solve. Social intelligence, which is interaction within other agents, and those could be computers or anyone else. It could be animals, it could be plants, it could be humans. And general intelligence, which, as I was saying, is about consciousness and theory of mind. This last point is probably what most people regard as AI. If we haven't thought about AI and we hear it, someone, oh, we use artificial intelligence to solve this particular problem, we think immediately about general intelligence. But most of the applications are happening in other areas, not in general intelligence. Some important definitions when we're looking at AI. I've just selected 5 of them, which appear over and over whenever we're using or whenever we're exploring or term artificial intelligence comes up. First one is algorithm. And this, I think probably a lot of you know about it. It's a set of unambiguous instructions that a mechanical computer can execute. Just follow a list. It's a list and we follow it. Second one, which not everyone might have heard about, is something called combinatorial explosion. And I'll tell you a little bit, I'll show you an example in a minute with the towers of Hanoi. This is a time to solve a problem, a time when solving a problem grows exponentially. And I'll give an example in a minute. And this is an example when we have a clear list of what we have to do, but the list is so enormous that it's actually not feasible to do it that way. And there might be alternatives, but finding them can be quite challenging. We also have something called heuristics, which are strategies or rules of thumb that worked well in the past. We don't know if they're going to work well again, but it's like a good place to start. An example of that is if I were going to look for Oxford as a search strategy, I might start in the UK. I might start in England. So I know that that's where Oxford is. Machine learning, which I think there's a massive overlap. People, whenever they think about artificial intelligence, they almost always think about machine learning. Machine learning is a series of tools. It's again a branch. You can think of a branch of artificial intelligence. As a statistician, you might contest that. That allows computer systems to learn directly from examples, data, and experience. So in a way, machine learning is a series of tools that we can use to take information in, manipulate it, and have outputs out that would allow us to solve a particular task. And importantly, that information, and this is why the massive improvement and developments in the last 20 years, if we have good data and a lot of information, a lot of data, the precision and the prediction that we're able to do can sometimes significantly surpass what we are able to do if we only have the usual or more traditional methods that are not considered machine learning. Again, I'll give you an example of that in a minute. And finally, the last definition I want to mention is something called overfitting. And overfitting is not that well known, but it's something that could happen and generally can happen when we have these machine learning methods that are very complex. If they're extremely complex models, extremely complex approaches to modeling the data, that model might fit perfectly the data that we have at hand, but might prevent us from actually using that model and then applying it to a different or slightly modified version of the question that we have at hand. And this is particularly the case when we, let's say, one example of this, when we predict the risk of something happening, when we predict the risk of, let's say, someone having a heart attack, which is one of the most common risks that in medicine we're interested in exploring and evaluating. If we model things to the extreme, we might be very bad at predicting the next person. Obviously, we use information from those that have had a heart attack. We use all the characteristics of those individuals up to the extreme, and then we're not able to actually get a good predictor, a good risk for a new person that comes in. So that is a fairly common problem with very complex models that we include. As I was saying, I was going to give you an example of exponential explosion. Here we have the towers of Hanoi. It's a problem that was developed by a French mathematician, Edouard Lucas, in 1883. And it's a relatively simple sort of game, let's put it that way. What we have is a series of disks in 3 towers, and the object of the game is to move each one of the disks. Let's see if I can pause this. No. Okay. As you can see at the start, we have all the disks in order. So from the largest at the bottom and all the way to the smaller. And the idea is to move all those disks from one tower in the extreme to the other tower in the other extreme, from the left all the way to the right. And the main rule is that whenever you can only move one block at a time, one disk at a time, and you cannot put a smaller disk below a larger disk. That's it. Okay. So if we have 3 disks, we can do the movements, and it's relatively straightforward. The minimum number of movements in order to get from, let's say, the left all the way to the right is 7. Okay, fair enough. When we have 6 disks, the minimum number of movements is 63. When we have 64 disks, which is it's linked to a myth of a story about an Indian temple in Kashi, Vishwanath, that contains precisely these towers of Hanoi, with 64 golden discs. And the idea is a priest acting on command of an ancient prophecy moves a disc every moment using these rules. And according to legend, when the last move happens, the world will end. But don't worry, because this is going to take 2 to the power of 64 minus 1 seconds. Let's say that it moves 1 per second, which translates roughly to 85 billion years, which roughly translates to 42 times the current age of the universe. So don't worry about it if you believe in that legend. And as you can see, it's just an example of exponential growth. We know how to do it. It's very clear. We can program this algorithm, but it just takes way too long to actually develop. So that's when things like heuristics, as I was mentioning, were to start. Changing the setup, changing the starting point might have an important effect in reaching a solution. I also mentioned that I was going to talk about what are the current basic approaches to AI. And I touched on machine learning just in general, but it's probably easier to explain the ways that AI in general as a generic term is being used in order to solve all the questions that I was mentioning before. And I've organized them into these 4: symbolic, Bayesian networks, nearest neighbors, and deep learning or neural networks. There's overlaps between these 4. They set up this. I've set them up this way because that's roughly how they happened historically, how they appeared in the AI landscape. But they are within these 4 overlaps. As I was saying, there are methods that belong to both. The methods to several of them. There are methods that can sort of stem from one and more involving another. So in a way, they're just, as I love to say this phrase, these are just a model of explaining how AI generally, the approaches of AI generally works. And as with all models, my model is wrong, but it's a very useful model. So that's why I'm presenting it here. So my model is wrong, but it's useful. Right. So I'll tell you a little bit about each one of these groups. The first one, symbolic AI. So symbolic AI is based on human readable representations of problems, extracting information from an expert, presenting it or creating what it would be a knowledge base, using some form of inference engine that will produce some form of outputs that we can then use as part of a user interface for advice once a query happens. So I'll give you an example of that. So here we have a very simple example based on logic. If the temperature is above, in this I did when we were in the middle of a pandemic. If the temperature is greater than 37 degrees, or your cough is new and continuous, or if your taste or smell is lost, then you go and get a test. And examples of this type of systems have been, or were actually very successful. Probably one of the best known is called Mycin, which was a doctor assistant providing expert advice about blood diseases in humans. And this is an example of the type of rules that Mycin used. The organism does not stain using the Gram method, and the morphology of the organism is rod, and the organism is anaerobic. Then there is evidence that the organism is bacteroidous, and it gives you a probability as well, in this case of 0.6. There was progress in this particular area, moving from just generally AI models that differentiate between different diagnoses. So they provide an answer. This is the answer. We realized that was actually a bit too rigid, so we needed to make it a bit more flexible. The next step was actually using machine learning methods that provide us not only with an answer, but with a probability of that answer being correct. And the third stage, or the third evolution of these type of methods, is instead of just providing an answer and probability, is saying, well, maybe it could be this. Why don't you go and search in this particular area? There is some evidence that these type of approaches are really useful for decision-making purposes, but instead of being useful to decide for the decision itself, they're useful to actually create the steps in the individuals that are making decisions, so you don't forget elements of it. So checklists have become very useful and are a byproduct of these type of methods. So there's still progress that are being done with this, with the limitations that I've already somewhat mentioned. And again, probably in the first phase in the 80s, this is when people talked about AI, this is probably what they were referring to, these type of approaches. The second approach, and this is closer to my heart in terms of, in a way, being a statistical approach, is Bayesian networks, so Bayesian representations. And what we have on the simplest way to describe Bayesian approaches is by this little graph that we have here. We have the likelihood, which, we have a prior, just start with a prior, which are generally our beliefs, where we think what we think is going to happen before we actually collected any information. Then we have data, represented by that histogram in the middle. And finally, we use what is called a likelihood, which is basically our understanding of what the data should look like, to combine this information between the data and the prior to then end up with a better understanding or a new understanding of where we are. I'll give you an example of Bayesian reasoning in a second, which we use or should use all the time in clinical management. A prior, as I was saying, is our general belief. So it's sometimes quite challenging to think about these things. We develop new methods about how to elicit that information, our beliefs, in order to create these priors, which have a mathematical representation. Let me give you an example of Bayesian reasoning as supposedly should happen. And again, maybe it's relatively topical, seeing what we've just gone through. And it's the use of diagnostic tests. So in this example borrowed from Loom 2003 EMJ paper, we have information about the prevalence of a disease. Let's say, for sake of argument, it's an upper respiratory tract infection. About 30% of the individuals would have it. And we have information about a test, which is not 100% accurate, which, as we know, after what we've just gone through, is the majority of the tests. The way the test is represented here graphically is everything in pink is what the test regards as positive. Everything in green is what the test regards as negative. So everyone that appears green will get a negative test. Everyone that appears pink will have a positive test. And as we can see, the test is not 100%. It misses 20 individuals. And it, 20% of the individuals. Misses 6 out of 30, and it also is not perfect in discriminating the negatives, those that do not have a disease. One way of thinking, and again, I imagine after what we've gone through, most of you are fed up with these type of terms, but the other way of thinking about these representations of information is by the use of what we call conditional probability, or more specifically, whether you're going to test positive if you're positive, which is a sensitivity. Okay, so out of 30 individuals, 24 tested positive. That's an 80% sensitivity. That's conditional probability of testing positive if you're actually positive or you have the disease. And then we have in this case, represented as 1 minus the specificity, which is the probability of testing positive if you do not have the disease, which is 20%. Does everyone more or less understand these things? And if we have the performance of the test, and if we knew the prevalence of the disease in a particular environment, we can use that information in order to decide whether someone testing positive is likely to have the disease or not. Does everyone follow? Let's try to do it with an actual example based on a cancer diagnosis in this case, and using a test called FOB, fecal occult blood, which is used as a screening test. So let's say in this example, the father has undertaken a test of FOB and it returned a positive outcome. And he asks you whether he has cancer. We have the prevalence of the disease, in this case, screening at population level in that particular age group returns a prevalence of 0.3%. So 3 in 1,000. And we also know from previous studies what is the performance of the test. In this case, the test correctly picks up someone that has cancer 50% of the time, so the sensitivity is 50%. And incorrectly picks up someone that does not have the cancer, does not have cancer, or the false positive rate is of 3%. Okay. So going back to my 2 screens, sensitivity is 50%, 1 minus specificity is 3%. I'm not going to test you guys. Don't worry. This is what it would work. So we have 1,000 individuals that are being tested. The prevalence is 0.3%, which means that 3 out of 1,000 will actually be positive, right? Not positive, will have cancer. And 997 will not have cancer. A sensitivity of 50% means that 1.5 out of 3, we could expand it to make it 15, but let's leave it at 1.5 out of 3 will actually test positive, and around 30 will test positive of those that are negative, because the false positive rate was 3%. If we add them up, we have that 31.5 will test positive out of 1.5 that actually have the disease. So the probability of having the disease if you test positive is about 5%. Okay. But the issue here, and that's why machine learning and AI is becoming important, is that this, as you probably realize, is not intuitive. This type of approach, this actually was tested by Gerd Gigerenzer and published in 2003, asked doctors with about 14 years of experience to do this particular, or was an example very similar to this. And the answers range from 1% to 99%, half of them estimating the probability of 50%. Okay, so it's not intuitive. It can be quite challenging. Almost like guessing. So that's when having some of these methods being integrated in our decision-making process might make it more useful, because it prevents us, or it allows us to not necessarily need to make that conversion in our heads. The third example, the third type of methods that I want to talk about is this called nearest neighbors. In a way, they are about identifying things that are similar, usually people. And I'm sure you've seen it all the time. If you're in Facebook, it will show you things that you want to see. If you're in Amazon, you'll have things like people that bought this also viewed. Okay, and in a way, it's about grouping individuals based on how close they are to each other. And this close relies on some form of metric to determine distance. And it could be your likes, for example. It could be in my type of examples that I have, the number of conditions that you have, your relative biomarkers that you have, your personal characteristics, to identify individuals that are more likely to be similar to each other. And that has been very useful. And we've all been involved, exposed to this, that with just a small number of likes and dislikes, you can actually classify individuals roughly, but quite easily in things like politics, religion, socioeconomic levels, and aspirations. And therefore, they're able to market to us in a better way, more direct way, let's put it that way. The fourth and last one that I want to mention is this called deep learning. And it's inspired by biological systems. What we have, this is a schema of what a basic neural network looks like. We have an input layer where most of the information is going to come in, and it could be things like age, your blood pressure, your socioeconomic status. So all those characteristics that we inputting. Then we have a hidden layer, and then an output layer. An output layer is the layer in a way that has the product of the output that we want. And it could, going back to this idea of cardiovascular risk, it could be telling me about whether you are at high, medium, or low level of cardiovascular risk. That might be my output layer. And my hidden layer is where the magic happens. That's how you can think of it. And the structure is based around the idea of each one of these circles being equivalent to our neurons, what we have in our brains in a way. The links between each one of the neurons will be our synapses. The strength of each one of those links will be equal to our weights. So we might have the links between each one of the things modified precisely because of the data or by the data. And then we have things like biases, which defines where the answer is likely to be. So it gives a limit about what things are viable and available or not. For example, as a simple example, I might say, if you are predicting a measure of blood pressure, it cannot be negative, for example, let's say. So it restricts the outputs that you have in. And finally, you have functions, which creates or describes when each one of these neurons will light up or not light up. So the simplest one would be if age is over 65 and your systolic blood pressure is over 145, then the next layer lights up. It's a step and it becomes 1. That might be the simplest one. But you can have all sorts of different things. It might be a continuous measure instead of just 0 and 1. It could be a value that is sigmoidal, or it could be a complete, there's loads of different types of functions steps that we can generate. And that creates quite a lot of flexibility with this type of methods, this type of tools. And the big change, why these have become incredibly popular, is this advance in the 2010s, where the availability of data and also the availability of new algorithms have allowed us to create or develop networks with further hidden layers, which have expanded on the flexibility that these things produce. Now, the downside of this is that they're very data hungry. So we need vast amounts of data for these things to actually work efficiently. And they're particularly useful when we have situations like imaging, and I'll give you an example later on, where the information is vast. Link, as I was saying, to development of new algorithms, and also in development in hardware as well. So for example, for these type of approaches, people tend to use GPUs, graphic processing units, instead of CPUs. I'm not entirely sure why, but they appear to be much better in terms of processing this type of models. Now, why are they particularly useful, particularly interesting? Is it magic? Well, in a way it is. What we have is typical machine learning. We have input, a human being will define what features to extract. It goes into a model and we have an output. So that's what would be the normal approach. We say, as I was saying before, age, systolic blood pressure, I want cholesterol, etc., etc. And that's what I'm feeding into the model in order to have an output. What deep learning allows is a automatic feature extraction. So I don't need to tell it what things to enter. It chooses everything initially and then decides which ones are the most useful and which ones will not. I'm not interested in having. Now, this has had a massive movement towards better prediction. But the problem is that we've lost interpretability. We don't have no idea what goes in and how. We might be able to interpret what's going out. But if we're talking, for example, epidemiology, when we're thinking about risk factors that are modifiable, what are we going to modify? And there is a movement nowadays to use deep learning, but then go a step back and try to understand how to interpret the outputs that we have. And the final example I want to give is evolutionary algorithms. Although they don't fall within those 4 strategies, they are probably very, well, we think quite very promising. The idea is that following sort of basically basic evolutionary computation to generate a series of algorithms that are populated initially. So we have all these algorithms. We can think of them as individuals. that are generated randomly. There's first each generation. And in step 2, we evaluate the fitness of each one of them. We measure how good they are a particular thing, and select only those that are fittest for the next step of reproduction. We breed new individuals and then replace the least fit with new individuals and go back to step 2. Now, as we all know, AI is being used everywhere. And here are just a few examples. We have in GPS tools and face recognition, in autocorrect, which sometimes we would like to stop, but sometimes it's difficult. We have in search and recommendations, in chatbots, digital assistants, social media, and e-payments. So it is here, and it's going to carry on being an important tool for our day-to-day lives. In healthcare, it's already available in many outputs. Here's just an example of the areas where AI is currently used and proposed to be used. And I'll just give 4 specific examples within these ones. So we can think of it appearing in training, in research, end-of-life care, treatment, decision-making, diagnosis, early detection, and keep you well. There's quite a lot of overlap between some of these. So for example, we can think of treatments being necessary to help with end-of-life care, and research being important in early detection, etc., etc. But these are probably some of the areas where we can think of AI being influencing heavily our approach to healthcare, health and social care nowadays. And I was saying, I'm just going to give you 4 examples of this. The first one is the use of wearables. We have things like different types of devices, skin patches, smart garments, smart watches, etc., that are used to measure a whole bunch of different types of characteristics in the individuals and are used in order to maximize something. In this case, it can maximize health. So we know, for example, some parameters that allows us to lead a healthy life. Classic examples would be blood pressure. We measure our blood pressure if it's within a certain limit. We think the chances of developing certain diseases are less. And so just like with blood pressure, we have other types of conditions. So we can measure this thing now often, but this has created a new source of disparity. We can think of the rich managing health while the poor managing disease, because all of these devices are expensive. Things like Apple Watch Series 7 is £369. Today, Fitbit Versa is 199 patches, and I have no idea what wearable patches are. So I'll have to find out. An area with clearly there's massive advances using AI is imaging. People have used deep learning methods to identify features and detect disease. As an example of this, about 10 years ago, maybe about longer than that, maybe about 15 years ago, I was involved in understanding how we monitor people with ocular hypertension. And they kept telling me, no, we're not that interested in the hypertension in the eye. What we're really interested in is in the retina. But there was no measure that we could use to monitor the retina, changes in the retina. It had to be an expert looking at it. With these approaches, all of that information that an expert used to have can be extracted using deep neural networks approach. It detects, quantifies a change, and if that change is enough to detect if someone has a disease or not. So I think that's when certainly the major steps forward in healthcare, in diagnosis and risk creation and risk prevention are going to happen. And the final slide regarding health input is the use of digital assistants to manage things like problems that we currently have regarding long waiting lists, with the systems not being able to, healthcare systems not being able to cope with the combination of the aging population and the increase in the cost of treatments. We have people living longer, but with more conditions. The size of the waiting list is growing massively. The pandemic only exacerbated them. The war is going to make things worse. So can we do something using things like natural language processing to improve the management and the interaction we have between patients, all of us, and people like receptionists, nurse assistants, general practitioners? Well, it's likely. But what could go wrong? Well, there's a few things that could go wrong. Again, I'm using the perspective of Michael Woolidge, and I agree with him. So these are some of the areas that he highlights. We think that things like employment and unemployment will change. So some jobs are more prone to automation. There's going to be new jobs that emerge. There's still lack of clarity about how that's going to pan out. It's a difficult time because I think we're in the transition process. We're going to have algorithmic alienation and changing the nature of work. We already identified that the gig economy is what we currently, many people live in, and that creates more precarious jobs. We have issues I was discussing earlier on regarding human rights, things like AI making decisions about who to treat and when, specifically in healthcare. We can have killer robots, which those already exist, drones used to fight wars. We can have algorithmic bias, and that basically means reinforcing stereotypes. So if the data has no one with a certain characteristic that has been given alone, then the next person that comes in and we use that algorithm will be rejected immediately because that they are not present in the data. And that's linked to lack of diversity. Only some people might be represented. We have fake news, showing you what you like, creating echo chambers, fake AI, which is generating tools that appear to be AI when in reality it's a human interacting. That has also happened. Importantly, we think that understanding the limitations of the tools that we're using and acknowledging them is critical in this evolution. Again, highlighting Michael Woolridge's book, The Road to Conscious Machines, The Story of AI. I've used quite a lot of his ideas. I used quite a lot of his approach to create this talk. There's also further reading. Besides that, obviously Wikipedia, the Alan Turing Institute, History of Artificial Intelligence, and Siri in my hand, who's the first in the land. It's a good one for business to illustrate the implications of artificial intelligence. And thank you. Happy to take this.
Excellent. So we've got time for, not much, but time for a few questions in the audience. I've got a few questions, but I'm going to let this lady here.
Thank you so much. That was super interesting. I was wondering what your perspective is on whether there will be a third AI winter based on the things you just talked about, the things that could go wrong. That's why.
The thing with prediction is you always get it wrong. But I'll say yes, it's a very high chance that there will be another winter of AI. I think part of the problem is that, and I guess I'm partly responsible as well, we all have jumped on the bandwagon of AI in applications and promising sometimes things that without really understanding the limitations of what we have. I think we need to be quite, we need to be quite careful about saying we're going to use these techniques and we think we're going to get there, but we don't know. While very often I perceive people saying we're going to use these techniques and we're going to get there. And there's no doubt we're going to get there. And the problem is that if we have funders giving the money for these type of approaches and 5 years, 6, 10 years from now, not getting the results that we said we're going to be producing in 2-3 years, then that's when, again, the contraction will happen. So I think it's a case of understanding what are the limitations, being honest with what we have, or where we're likely to be, and making sure that over-promising, it's difficult because the nature of the environment that we're in, we understand that it is quite challenging to actually not present the best case scenario. So that's why I think that the chances of it being another winter are likely, are high, but that's in a way the common denominator in most applications in general. So it's not only AI that has these things. We all endeavors in human activity tends to have these fashions and then they fall out of fashion. So it's quite likely they will be.
this lady here.
Possibly building off that question, which was, will there be an AI winter? But another question would be, should there be an AI winter, in the sense of just the sheer extractive processes that are needed to sustain the machines that from a kind of the climate perspective, which is really quite unsustainable. So should we start to actually restrain, measure ourselves, factor that in, and also look beyond what might come after that?
That's a very interesting question. I'm afraid that's beyond my understanding in terms of what proportion of the total energy, let's put it that way, is used by things like servers, by us using these technology in our phones as well. There's a really interesting book about how the world really works. It's by a professor in Canada on specifically interested in oil. I'll dig out his name for you in a second. And he talks about different the real costs of, for example, eating a chicken, or the real cost of having a loaf of bread, or the real cost of creating a computer. And I think there is probably where I would have a look first, in order to understand whether AI has such a massive footprint that it'd be worth. It's a bit of a cost-benefit thing, whether it's worth actually stopping some of the developments that are happening, or on the contrary, that might provide us with some of the tools that we need in order to transfer the bigger consumers of energy to things that are more sustainable. So I wouldn't be able to answer that, unfortunately.
I'm going to finish with one question. I always take one thing away from a talk that makes me think, and actually with the definition. Because often you talk about things like artificial intelligence and you go, yeah, it's that, and actually you don't even think what defines it. We talked about it in terms of facilitating behaviors that our brain, or what we do, so that computational issues that the brain did. And it made me think about, like, well, drugs are about chemical reactions in the body, and there are agonists and antagonists. So it seems to me, if we talk about artificial intelligence, is there one thing you think that will help us do something, and maybe one thing where artificial intelligence will help us stop doing something? Because we never think about the antagonist approach in what we do.
As a negative thing?
Well, some of the drugs stop you doing something.
Yeah.
Some of the things we do as humans, which are actually bad, can artificial intelligence help us stop doing the bad things as well in the way we think?
Well, I mean, a perfect example of that is the use of Google Maps, for example. So if you use Google Maps, that allows you to get to a place very efficiently, but doesn't allow you to remember how to get there. So they did some tests to individuals precisely using these devices, and then they took the device away. And so they randomly assigned people to those that use the device and others that did not use the device. And those that did not use the device could not find their way back afterwards. The ones that used the device initially could not find their way back. So that's an example of, we win on some things, but the other things are obviously we lose from the fact that we're using these particular tools. So yeah, there's always advantages and disadvantages depending on how you use them.
All right, on that note, I'm going to say thank you very much for that interesting and excellent talk. And I know some people have got guest dinner to go to, but thank you very much, Professor Rafael Perera.